Our Exploratorium crew in Antarctica just arrived at the South Pole, and today we connect with them live from that location for the first time. Hi, I'm Kate O'Donnell, your host for this special Ice Stories webcast. I'd like to welcome our audience here in the studio as well as on the web. These series of polar webcasts and online updates are made possible by a generous grant from the National Science Foundation and celebrate the International Polar Year. Today we are connecting with our Exploratorium hosts and producers in Antarctica, Mary Miller and Ron Hipschman, who are live at the South Pole with some very special guests. Let's see if we can go to them now. Ron, Mary, are you there?
We're here, Kate.
We're here.
Hello, San Francisco.
Hello, South Pole. I just want to explain that due to our satellite connection, we have a slight delay, so please bear with us on that. Now, Mary, Ron, you guys have definitely been up to some fun things, including a trip down south. You want to tell us a little bit about it?
Well, yesterday we took off in an LC-130 cargo plane. There were 6 of us on the plane, so we had a lot of space. We were very lucky, and it took us about 3 hours to get here to the South Pole. We were given our rooms, we had a nice meal, we had a chance to go out to the IceCube experiment and check that out. And then we got a good night's sleep and prepared for your webcast.
Great. Well, before we go, I know that you have a special guest standing by with you there, but before we go there, I'd like to introduce you to some other very special guests that we have with us today. We are joined by a classroom in Norwich, England from Framingham Earl High School. So hello to all of them. So we'll be checking in with them more in a few minutes for some questions. But in the meantime, if you'd like to introduce us to the guests that you have there.
Well, our special guest here today from the IceCube experiment is Mark Krasberg, and we'll bring him in here. There he is, rolling onto the set we have here in the conference room. Mark, you've been with the IceCube experiment for quite a while now, haven't you?
5 years.
5 years. It's a very interesting, it's a kind of different kind of telescope. It's looks for, well, we'll get a little bit into this a little bit deeper, but you're looking for neutrinos.
Yep. We're looking for high energy neutrinos, and it's a very weird telescope. It's looking for high energy neutrinos that are coming through the Earth, and we're hoping to discover something that basically no one could predict. Okay, every time people have built higher and higher energy telescopes, they've discovered things that no one expected, and so that's what we're hoping to find something that in the universe that out there that no one actually was able to predict before.
So one of the things that you would be able to detect that we have seen before is something like a supernova. Here we have a picture of a supernova we can show you. It's a little harder for us to switch here, so we'll be a little bit delayed. There's a picture of the Crab Nebula. This was a supernova that was observed in 1054 AD. We know that because Chinese astronomers documented it very well, and this kind of event would be seen by IceCube if it happened today.
Right. We will definitely see some supernova in our galaxy. We're looking for, there are objects in the universe that we think might be producing high energy neutrinos, and so we're looking carefully at those objects to see if we can see neutrinos coming from them. And again, there are objects out there like, there's these supernovae that occur, every few years, and we're hoping to see one. And so basically, we're basically looking at a high energy realm, looking at the universe in a high energy region. We're using neutrinos to study it. We're hoping to see something amazing out there.
So you're doing this real research. Sort of like Werner von Braun once said that research is what I'm doing when I don't know what I'm doing. And you're doing research where you really don't even know what you're going to be seeing.
Right, that's right.
It's really exciting. Now, you talked about neutrinos. What's a neutrino?
A neutrino it's chargeless, it's almost massless, it passes basically right through everything. Everyone out there, you've got like 10 million neutrinos going through your thumb every second. They don't do anything to you, and they're really hard to detect. And so one way to actually detect a neutrino is to build a really large detector. And so that's what we're doing here. We're actually instrumenting 1 billion tons of ice. We're building a detector over a volume of 1 cubic kilometer. And that gives us a chance to see these neutrinos that are really, really hard to detect.
You have to build it big because the interactions are so rare.
So rare, yep.
Even though there's...
So our detector, most of the neutrinos go right through our detector, and we don't see them.
There's trillions and trillions and trillions of neutrinos every second going through your detector, but you only see very few of them.
Very few. We see right now, we're seeing about 50 a day.
50 a day, that's a lot. That's compared to previous experiments.
Right, well, and our detector is getting pretty big. Right now it's half a cubic kilometer, and it's growing every year as we put in more of these digital optical modules in the ice.
So let's take a look real quickly at what actually happens to the neutrino when it's going through the ice that makes it detectable for you. We have a little slide here. So coming from the bottom, and we'll explain that a little bit in just a moment, is a neutrino. It's coming up through the bottom through the Earth.
Right.
And it hits an atom. What happens then?
And then basically there's a physics interaction that takes place, and a high energy muon typically comes out. And that's actually a heavy electron. It's a charged particle. And when it travels through the ice, it actually gives off light. And we are putting thousands of light sensors into the ice to see this light. The light is called Cherenkov radiation. It's a very pretty blue light. And our modules pick up that light, and from that we can infer that there was a neutrino.
This Cherenkov radiation is the same blue kind of light you would see in a pool at a nuclear reactor where they store all the rods. A lot of people have seen those pictures.
That's
this pool glowing blue, except your detector you're not getting that kind of bright blue because your particles are much rarer.
Right. We don't typically. There's not very much blue light in there, but our modules, our sensors are very sensitive, and we pick up small amounts of this light, and from that we can actually reconstruct the path that the neutrino took through the ice, and we can also determine how much energy the neutrino had.
So you have a lot of these detectors. They're hung on strings underneath the ice. Here's a simple diagram. At the top of the ice, there are...
we have modules on the top that help us actually... there's a lot of particles coming from above, right?
Right.
A lot of cosmic rays, a lot of muons come from above through our detector. So we have a huge signal of events coming from the surface, coming up from above. And then we have a very small signal that we're very interested in, which are these neutrinos that are coming from below. So our telescope is actually looking into the Earth.
So there's lots of strings of these things.
Right. We're actually putting in 80 strings, and each string has 60 modules. And so far, up until today, we've put in something like 47 strings over the last 4 years. And eventually, there's going to be 80 strings with about 5,000 of these sensors in the ice.
So let's take a look at these sensors. You have one here.
Yeah, this is one here. So this is a digital optical module. It's basically got a big inverse light bulb underneath called a photomultiplier tube. Those come from Japan. And they basically collect the light.
So the light comes into the bottom of the detector here.
Right.
And this thing here amplifies...
It amplifies the light.
Well, it changes the light into electricity, electrical pulses.
That's right. And then we have basically a computer on top. We have a main board and some calibration flasher board, a high voltage board for the PMT. But basically we have a computer on top that takes the signal from the light and sends it up to the surface through a cable that's hooked up to a big in-ice cable that goes all the way up to the surface. So these modules go down 2.5 kilometers under the ice.
That's quite a distance underneath the ice.
That's right.
So this is one module. There are 60 of these per string, and there are 80 of these strings. So
eventually there'll be roughly 80 strings.
So you're talking about 5,000 odd modules. That's a lot of modules.
Yes.
So And you're burying them 2.5 kilometers underneath the ice. That seems like an amazingly difficult task. How do you do that?
Right. We have an amazing hot water drill. So basically, we make a hole that's big enough for a person to fit inside.
And we're looking at a photo now of the, what did you call it? The drill camp.
This is the drill camp. So in the photo on the right, we have lots of heaters. So we basically produce a lot of hot water. On the right, you see the heating units with a lot of steam coming from them. There's a lot of hot water. In the center, there's a large black hose reel. It's a 2.5 kilometer hose. And in the top left of the picture is a drill tower. And basically, we feed hot water down where we're drilling a hole. And in about 36 hours, we can drill a hole down 2.5 kilometers under the ice.
Let's take a look at that. Let's take a look at the drill itself.
This is a picture of the drill. We end up with a column of water that goes down, 2.5 kilometers, because basically all of what we end up doing is melting the ice. And then we pull the drill out. So I think
there's a movie I think we have.
This is a movie of the drill in action.
It's kind of hard to see it move, so he's going to put a piece of tape on the drill as it's going down, so you can get an idea of sort of how fast it's moving.
Right.
So there you can see that piece of tape is now at his shoulder height, and
after a day and a half, then we're down at 2.5 kilometers down.
It's going to be at his waist pretty soon. So that's pretty fast for melting a lot of ice like that. And the next thing I think we have an animation. Describe what's happening here.
So actually, at the South Pole, you have a firn layer, which is basically compacted snow, and we use a fairly normal type of drill to make a hole through that firn layer. And then underneath the firn layer is the ice, and this is now the hot water drill, basically drilling a hole down through the ice.
And then that goes down 2.5 kilometers.
And then at the end, we pull everything out, and we have this column of water, and it actually takes a while for the column of water to freeze back. And during that period is when we actually drop our string of sensors down.
So here we have a sensor moving down into the ice, a dome you can see from above at the top of the hole. There it is a little further down.
Right.
And
so we basically drop a string of 60 of these modules down to the bottom of the hole.
There they are, ready to be dropped into the hole, whole bunch of them. And tell us about why Antarctica? Why are you doing this in Antarctica?
So in order to see this Cherenkov radiation, right, it's light, you need a clear medium, and it needs to be large. And so there's basically two types of places you can do this. You can do it in the ocean, in the water, and you can do it in the ice. And we actually do it in the ice. The ice underneath the South Pole surface is incredibly clear. We have little LEDs on our sensors that we can flash, and the light will travel. They're on the top part of the modules here. The light will travel 600 meters, 2,000 feet. Our sensors 2,000 feet away will actually see a dim little light flash from one of these LEDs. The light underneath the South Pole is incredibly clear, and that's exactly what you want. That's exactly what you want in order to see this Cherenkov radiation from far away, because that actually makes our experiment better. The clearer the medium, the better.
So I just have a couple more special slides. We went out to the IceCube yesterday, Mary and I, and Mark was gracious enough to allow us to sign a dom. And so here I am kind of signing the dom. And there we go. So this is Ron Hipschman from the Exploratorium. I'm going to hand it over now to Mary Miller. Mary.
Hello, Kate. Can you hear us?
Yes, I can. That's great seeing those autographed DOMs. We've got another DOM here in the webcast studio for all of our guests here to be able to see and explore too. So thank you so much for being able to help us get that.
So, Kate, do you have some questions from the audience, or maybe from the, I think you have your special guests?
Yes, we do. We have, we're going to go to one quick audience question here live at the Exploratorium, and then we're going to go to our class in England for some questions.
I was just curious, how do you know that the Cherenkov light that is being emitted is coming from the neutrino hitting an atom? How do you know it's a neutrino and not something else?
So, when the particle's coming from above, we don't know that. In fact, most of the time it's not from a neutrino. But when the particle's coming from below the detector, which is coming from, say, the North Pole, from through, it has to go through the Earth. And what we know is that the only type of particle that will get through the entire Earth without stopping is a neutrino. So when we see particles coming from below, we actually know they're neutrinos. There's nothing else they could be.
Great.
And our detector determines the direction of going.
Great. Well, thank you. That's a great question. We're going to go now to our school in England, in Norwich, and see if they have some questions for us. Steve?
Okay, we have a question here from Chris from Mars. He's got a question regarding the sensors.
Yeah, how much do the sensors cost?
How much do the sensors cost? Is the question.
Each sensor costs maybe close to $10,000. So it's a very, it's a big budget experiment. The experiment is, at the end of the day, it's going to cost about $270 million. And that's funded mainly by the National Science Foundation, but it's also funded by other groups in Europe. They put in a lot of money, and then other people in other parts of the world as well.
I think we're switching students here.
Okay, so our second question comes from Kate in Leach.
Will you use IceCube to study the newly discovered black hole in the centre of the Milky Way?
Did you get that question?
You could repeat the question.
No.
Will you use IceCube to study the newly discovered black hole in the centre of the Milky Way?
Will you be able to use IceCube to study black holes in the Milky Way, I believe is the question.
So what we're very interested in is finding out where the hydrogen neutrinos are coming from. And so one candidate would be black holes. And so we would be very interested in finding out if neutrinos were coming from an area in the universe where we think there's a black hole.
Okay, our next question comes from Peter Quattro. Okay, nice and now, please.
Does experiencing 24 hours of sunlight have any impact on sleep?
Does experiencing 24 hours of sunlight have any impact on your sleep?
I slept very soundly last night. They have blackout curtains on all the windows so you can make the rooms really dark. And so all you have to do is keep track of your watch and go to sleep when you're supposed to go to sleep and not pay attention to where the sun is, because the sun is always up. Right now it's about almost the summer solstice in the southern hemisphere. So the sun is always up about 23 degrees in the sky, and it just goes around and around and around every day. It'd be a terrible place to grow sunflowers because they follow the sun.
The thing that affects your sleep is the altitude, right? We're sitting on top of 3,000 meters of ice, about 10,000 feet of ice. So we're at pretty high altitude, and that's actually the thing that makes it difficult here.
Great. Well, I think that we can take one more question from Norwich for the moment, and then we will come back to you for some more questions at the end. So let's take one more question for the moment, though.
Okay, Chris from Mars wants to ask a second question. Okay, Chris.
Have you had any problems with the construction of the IceCube?
Did you get that? Have you had any problems with?
just with IceCube. IceCube's going really well this year. We're actually ahead of schedule. We're several days ahead of schedule now. And so everything's going really well. No one, it's a slightly dangerous thing to do, drilling these big holes in Antarctica at the South Pole, and no one's got hurt, and everything's going really well.
From the webcast team, I don't think we've had that many problems. We've just been working real hard for you.
They're actually doing really well because often day after they get here.
Great. Well, we're very glad to hear that things are going well for now, and we're going to toss it back to Mary for the moment, and we'll come back to Norwich for some more questions at the end.
Hello, Kate.
Hi, it's great to see you. It looks like you have some extra special guests there with you. You want to let us know who they are?
Sure. When we got in yesterday, I took a little trip over to the camp where the Norwegian-U.S. Traverse is happening, and I ran into some friends of ours. Zoe Corbel is in the middle. She's an Ice Stories correspondent who we last saw corresponding from Greenland. Tom Newman is sitting right next to me. Also, we talked to him in Greenland. And Ted Scambos is on the end. We talked to Ted and McMurdo before he came out here. So welcome, you guys. So I thought we would just tell you a little bit more about the Traverse. They just all walked over here from their camp. Actually, the South Pole right now is full of people, both in the station and camps all around. The acclimatization camp for AGAP is here. There's a couple Traverse teams. There are just people scattered all over the place here. It's I think yesterday there was over 300 people, which is way beyond the normal capacity for the South Pole, but we're having fun rubbing elbows. So I thought I'd first talk a little bit to Tom. Now, Tom, this Traverse seems very epic. It's a 2-year traverse across the ice from the coast to the pole and back again. Can you tell us just a little bit about what it is that you, what science you're doing and what the purpose of this trip is? It's an international polar year project, yes?
It is an international polar year project. It's a collaboration between Norway and the United States, and it's a project that neither country could have done individually. There's 6 U.S. institutions and 8 Norwegian institutions that are partnering together, as well as partnering logistics between things that the Norwegians can provide and things that the U.S. can provide. The scientific goals of the Traverse are to explore an area of the continent that's visited very rarely. It was last visited by science in the 1960s. And what we'd like to do is to understand how this part of the continent is changing, how it's getting larger or smaller through time, and better understand its role in the climate system and how it's interacting with the atmosphere, with the ocean.
Now, I know that the route that you took last year to the South Pole is different than the route that you're taking back. We have a map, which may be a little bit difficult to see, but if we switch to that, maybe you can explain a little bit about how the return trip is different and how you and what you are doing on the return trip that you couldn't do on the trip over.
Sure. On the trip over, we were following one of the ridges, along one of the ridges on the Antarctic ice sheet. The ice sheet is kind of lumpy, and there's high spots and there's low spots. Last year, we were along a high spot. This year on the return trip, we're going to follow a lower route that crosses this area known as the Recovery Lakes area. And these are subglacial lakes. It's liquid water down at the bottom of the ice sheet that seem to have a control on where the recovery ice stream, a stream of really fast-moving ice, starts. And it's pretty unusual to be able to examine a site like this in the kind of detail that we'll be able to. We're going to spend about 2 or 3 weeks in the Recovery Lakes area doing a whole variety of measurements to understand that interaction between the slower moving ice in the interior and this faster moving ice stream that really carries a lot of ice out to the ocean.
I wanted to bring in Zoe here as well. Yesterday we were over talking to you, and you explained to me that on the trip over you didn't quite make it to the make it to the pole as intended, you stopped. And you sent us a little video of that. Why don't we show that a video of what happened and how you solved that problem?
Right, so last year was actually a heroic effort in terms of logistics. 7 of the differentials on the vehicles were broken and had to be repaired in the field in the cold by the mechanic from Norway named Kjetil. And so, and then 2 gearboxes also broke. And what eventually stopped the traverse 350 kilometers from South Pole was that there were no spare parts left on the planet. We had run out of all of them. And so, we left everything in an area that was called Camp Winter, and so the vehicle spent the winter there. And then this season we flew in and set up a large tent. And so here you're looking at video of the mechanics working inside this large tent. And it's mind-boggling how large it really is. It's about 15 feet high. It's large enough to fit one of the vehicles in with the cab tilted up, and that's what you're looking at here. And then it was warmed to a little bit less than room temperature, so it was comfortable for these guys to work. And they fixed and modified all 4 of the vehicles so that this year we wouldn't have the same problems that we did last year. And last year, even with all these problems, because of Kjetil and because of the logistics work done by the Norwegians, all the science was done that we had planned to do for the most part. And so it was a successful season, even though we didn't quite make it to pole. So this year we were able to fix the vehicles and then drive in with very, very few problems.
So I know Zoe and Tom, you guys caught up at winter camp with them and then came into pole. So you'd actually made part of the traverse meant last year for this year. You sent us a video of that. Let's look at that, and you can tell us, what is it like to be on this big wagon? It's like a wagon train on the ice.
It basically is. We're basically gypsies. We carry everything with us. So you can see these are the vehicles. We have 4 vehicles. We have a sleeping module with bunks. We have a living area with a really nice table and a kind of like IKEA-esque kitchen. So everything's comfortable. And we're carrying all our science equipment along, almost all of our fuel, our food. And our top speed is 10 kilometers an hour or 6 miles an hour. So if you could basically be jogging alongside the traverse for a little bit, but it's really amazing the amount of cargo that we're able to carry and just how comfortable it really is.
Is it a bumpy ride, or you're sitting in these machines all day? Are you warm? Is it bumpy? Can you read, sleep?
Yeah, so to drive here, we actually drove 24 hours a day in shifts of 6 hours with one person driving and one person sleeping. And it is bumpy. This area that we're going through in the video is actually relatively smooth, but it's not so bumpy that you can't sleep. It's a little soothing because you're going slow enough that you're not, it's not going too fast, you're not too jostled. You can read, and it is pretty comfortable, and I enjoy driving quite a bit. So.
Now I know that on your trip out over the recovery lakes, you won't be driving 24 hours a day. You'll be driving to a place, stopping and doing some work. So I think the last video you showed us, Zoe, was pulling into the pole. Maybe you can talk a little bit about that and what you've been doing while you're at the South Pole.
Yeah, so after driving, we drove for 4 days straight to get here, and I think I was definitely sleep deprived, but there was definitely a feeling of euphoria. One of the mechanics, the hero of last year, Kjetil, has been involved in this traverse for 3 years, and he was involved with a fuel cache a couple years ago and then last year. And so for him to finally get to drive into South Pole was an amazing feat. And I know John, the operations manager, was also very happy. And it's for historic reasons as well. This is one of the first major Norwegian exploration to reach the South Pole since Amundsen. And so it means a lot to them historically as well as just personally. And then that the vehicles were performed so well in our drive out here was another. I think everyone was really happy to make it here.
So Ted, you missed this part of the trip, this fun part of the trip.
I let him work the bugs out first. And then,
So you've been here for about a week. What sorts of things have you been doing to keep busy and to prepare for your science?
The whole team has been getting ready to go, getting ready to pack all of the science, get the science to work together, because we have a lot of instruments operating at a lot of different frequencies. So we have to make sure that they can all work together without producing interference with each other, testing the equipment, seeing where it's all going to fit and how it's all going to be strung out on the train. It's a different setup this year from last year because there's a bit more focus on geophysics because of these lakes, which weren't a feature of the Traverse last year. So we'll be doing some different geophysics and a couple of different radars, and we've been trying to get all of that ready to go in the next few days.
So Tom, are you raring to go? When are you gonna pull out of here?
We're hoping to pull out of here on Monday or Tuesday of next week. When we were coming into to South Pole, we had talked a lot about the schedule and how long it would take, and I had guessed 10 days from my own planning, and people were like, "Oh, that sounds like a long time. I don't think it's going to take that long." We'll see. I think it's going to end up being. I think it will end up being 10 days.
So you have any major celebrations planned for when you arrive at Troll Station, the Norwegian station near the coast?
We won't have to plan them.
We won't do the planning, but there is a group from the Norwegian Ministry of the Environment will be down there to meet us, and it sounds like a group from the BBC as well, and a few other media outlets. But mostly I'll be looking forward to having a nice long hot shower and doing some laundry.
Well, it's really great to talk with you. I'm sure we'll be seeing it in the news when we get back. You guys are going to roll in there sometime in mid to later February, so we'll be looking for you. So Kate, I'm going to give it back to you and see if there's any questions from the audience there or in England for our Traverse team.
Great. Well, Zoe and Ted and all of you, Tom, it's great to see you. I'm glad that you made it there. And yeah, we're going to go to some questions. We're going to go to Norwich really quickly and take one or two more questions there. And we'll see if we have any questions from our audience as well.
Okay, so we have a question here from Matthew Boyle.
Digging the IceCube, is it doing any harm on the environment?
Is digging an IceCube doing any harm to Antarctica's environment?
So I think that's a question for either for Zoe or for Mark. I think the question was whether digging into the snow and digging for this ice in Antarctica causes any harm to the environment.
We try to be as clean as we can, and when we're especially drilling or digging a pit, the saying here is that if there's a hole, that nature is going to take care of it, because there's enough blowing snow that eventually it will be filled in. I dig fairly shallow holes in the snow, so usually 2 meters, and I fill those in when I'm done and pack them down. And Mark, I always take GPS measurements of where I've worked so people will know. And we try to be as delicate as possible. The holes will close up eventually, because and so that's also not a problem. Nature, and if nature will take care of itself in a little bit.
I just want to add that the standards have gone up a lot in the last few years, that we really, unless we're leaving a scientific instrument that we plan to come back for, we only leave tracks in the snow when we drive through. And within a couple of days, even those are gone. It's a very clean operation. That wasn't always the case in the U.S. program and all of our Antarctic programs, but now it really is. People have really gotten it to where we barely touch the continent anymore.
So I think we're going to take one more question from England, and then we can keep the connection open so you can ask some more questions. But we're going to wrap it up here and take one more from you guys.
Okay, Kate. The question comes from me, the teacher, Mr. Rackley. I quite often teach about katabatic winds, but I've never actually experienced one for myself. Can you describe to me what a katabatic wind must feel like in Antarctica?
Okay. So a katabatic wind is a wind pattern kind of unique to large ice sheets. And what's happening is that the ice surface gets very cold. The sky is very clear often. The sky is also very dry, so it radiates all of the heat off of the surface, chills the air on the surface, and that starts to slide off of the continent under its own weight. It's denser than the air above it. So that's one of the features of our trip this year. We're going to be down lower in the katabatic wind stream. Now where we're going, it's more of an annoyance. It's a constant, steady, light breeze at -30 or whatever temperature we'll see on this trip out there. By the time you get to the coast, though, that wind that's starting from the very top of the continent channels into these narrow bands as it heads out over the glacier tops. And you get these very abrupt, instantaneous 100-mile-an-hour, 150-mile-an-hour winds coming down the glacier troughs, draining all of this air off of the continent. It's like its own atmospheric layer, this katabatic wind layer. It's just the bottom, I should say, 20 or 30 meters of air that's really cold and slides off the continent, well, constantly, especially in the winter, but constantly.
Well, great. Thank you so much, Steve, and your class for all of those wonderful questions. Again, if you hang tight with us, we are going to keep the connection open after we sign off so you can have some more conversations with our folks in the South Pole. Before we do sign off, I wanted to go to one more quick question from our audience here in the Exploratorium.
Yes, I was curious, beyond the science that the U.S.-Norwegian team is doing on the ground there, I'm curious who's looking at just the challenge of the traverse, because it seems like it's an analog for a lot of extreme environments and plans for traveling to Mars, etc. So do other research organizations look at just the challenges of what you're doing and ask you to report on that as well?
I guess I could try to answer that. I'm the expedition leader this year, the field team leader, and so I kind of have to have the big picture of how this is all working and how it's fitting together and trying to keep a handle on that. We haven't been working with any other groups who are sort of studying the traverse as a microcosm of a small group working together in a hard environment. There have been those kind of studies in the past, for sure. Our project isn't really unusual in that regard. I've been in a number of other small field camps far away from support, working outdoors. But that's a good point that you raise, and I'm not really sure what those studies have come up with. I've almost not wanted to know because I want to be able to do this again. And if I knew too much about what it's doing to me psychologically, maybe I wouldn't come back.
All right, well, thank you so much, Mary and Ron, and thank you so much to our guests in the South Pole, Mark and Zoe, Tom, and Ted. It's been great to see all of you, so thank you so much for joining us.
Thanks, and bye-bye from the South Pole, bye-bye Exploratorium audience, and also the students in England.
And thank you so much to them as well. Please join us for our next webcast, which is coming up. Say goodbye. It's great to have you with us. Thank you very much, Steve, and your whole class. So please do join us for our next webcast coming up tomorrow at 1 p.m. We'll be talking with Dr. Slavik Chulicek about his Under the Glaciers project, studying subglacial lakes. That's it for now. We want to thank the National Science Foundation, the Office of Polar Programs, the Moore Foundation, the McBean Family Foundation, and the Jim Clark Endowment for Internet Education for their support and making ice stories possible.